Okay, my friends, today we'll be covering chapters 2.4 and 4.2, all things second derivative. Okay, okay. So first, let's do a definition. Definition, let f of x be a function with f prime x as its derivative. Then f double prime x is the second derivative found by deriving f prime x. That's it. Pretty easy, pretty straightforward. Here's some notation for you guys. You can write it as f double prime x. You can write it as d2y dx squared. The reason why this works is because you are taking the derivative with respect to x of y twice. That's all. You can write as f double prime, especially if the function is written as like f of x. This would be used if the function is written as y equals. You can write as y double prime. I don't love it. It kind of looks like an 11 to me, but if you do that, that's fine. And you can also write as y2. I don't recommend this because it looks like y squared. If you're a physicist, you might write it like this, and I hate it. Don't do that. Okay. And this is also known as, because it's the derivative of the first derivative, is also known as the rate of change of the rate of change. Okay. All right. I'll throw another definition at you. You know what? How about this? Extra credit. If you watch this video, yeah, if you watch this video, you have up until March 27th, 2026 at 6 o'clock p.m. to email me a drawing, oops, of what you did during spring break, and this will be worth +1 on your next quiz, or on your sixth lowest quiz. Okay? The reason it's the sixth is because it dropped the lowest to 5. So if you email me a drawing of what you did during spring break, doesn't even have to be good. I love stick figures, all right? I will give you an extra point on your sixth lowest quiz. So if your sixth lowest quiz is a 4, it's a 5 now. Okay, and this is going to be like the sixth lowest quiz out of the whole entire semester, okay? Not just what we already have. So, extra credit opportunity for anyone who watches these videos, which you should be doing. Okay, anyway. Oh, this also applies for my in-person students as well. Okay, okay. Um, anyway, definition, point of inflection or inflection point. It's worth noting that not all these are actual points, and we'll get into that, okay? The point of inflection of the function f of x, oops, f of x is all x values where f double prime, okay? Some of y'all do not use prime notation, or any notation for that matter, and you need to start doing that because I don't know what you're yapping about. Where f double prime of x is equal to 0, or f double prime is not defined. Obviously, f double prime is also not defined wherever f is not defined, because discontinuities carry over. So, all right, that's it. That's how a point of inflection works. You can also view it as the critical points of f prime of x. And obviously, right, once you have these x values, so like let x not be a point of inflection, you know the y value in f of x, if defined, is x naught comma f of x naught. Okay, so like, for example, if you have a function that looks a little bit like that, right? And there's like an asymptote right here, and then it goes like that, right? I'm going to tell you that there's a point of inflection here, and there is a y value. So if it's defined, you need to find the y value. So it's going to be x naught comma f of x naught, and it's going to be undefined here. So you're going to have like an asymptote at x1. Okay, so make sure to separate whether it's a point of inflection because it's f double prime is equal to 0 because there's an asymptote. It's very important. Okay. Yeah, that's it. Um, yeah. We'll talk a little bit about the relationship between the derivative, the first derivative, the second derivative, and the original function as well. Okay. So let's call it a theorem. Relationship between f, f prime, and f double prime. Okay. Again, notation is important. That's why I've been taking off points. Because if you tell me all of them is equal to f, one of us is lying, that ain't me. All right. So first, we know that when f prime is greater than 0, we know that f is increasing. Easy enough, right? In fact, what I'll do is I'll handle this in pink. I'll write this in pink. Is increasing. We also know that when f prime is less than 0, f is decreasing. Okay. So this tells us the relationship between f and f prime. Okay. So now we know that when f double prime is greater than 0, right? F prime, right? The derivative, right? Rate of change of the rate of change, rate of change. Please keep track. You will get lost if you do not. Okay. When f double prime is greater than 0, f prime is increasing. Okay, easy enough. When f, oops, I don't need that one. When f double prime is less than 0, f prime is decreasing. Okay. Now, you now want to tie f to f double prime. Okay. So that means we also get an f is increasing or decreasing at an increasing rate. You decide f is increasing or decreasing by the first derivative, and then you decide whether it's increasing or decreasing at an increasing or decreasing rate by the second derivative. We'll make a little table, it's going to be okay. And similarly, f double prime is less than 0 means that f is, again, increasing or decreasing. Please don't write increasing or decreasing. You have to tell me whether f is going up or down, okay? Or decreasing at a decreasing rate. Easy, right? So as a table, right, if you have f prime is greater than 0, f prime is less than 0, and then you have f double prime is greater than 0, f double prime is less than 0, and you have the actual function you're interested in right here, right? When f prime is greater than 0, we know our function is increasing. Increasing at a f double prime is greater than 0. So increasing at an increasing rate. Okay? To be very clear, this is the behavior of f. Okay? F is increasing at a increasing rate. Okay, cool. When f prime is less than 0, f is decreasing at, when f double prime is greater than 0, decreasing at an increasing rate. Okay? Similarly, when f prime is greater than 0, f is increasing, and when f double prime is less than 0, it's increasing at a decreasing rate. Decreasing rate. And finally, when f prime is greater than 0, f is, less than 0 is decreasing at, and when f double prime is less than 0, decreasing rate. Okay? So take a minute, marinate on that. I'll show you an example. Okay, so let's say that this is, actually, let's do two. Let's say this is your first function, right? And let's say that this is your second function. Would you agree that both functions are in fact increasing? For a function to be increasing, it has to go, up, right? Definitely going up, right? Now the question is, which function is increasing faster, right? We know that this function is linear, which means its rate of change is constant. This function is exponential, so the rate of change is not constant and is in fact faster than constant, right? So although both functions are increasing, the purple one is increasing faster than the yellow one, right? So the purple one is increasing at an increasing rate. The yellow one is increasing at a constant rate. Do you see the difference? Okay. Another way of looking at it is a function like this is most definitely increasing, but it's increasing at a decreasing rate. It's diminishing returns, if you will, right? For those of you who work out, plateauing, right? Versus a function like this. which is increasing at an increasing rate. Every time it goes up even more than it did before, right? Now, let's do some examples of points of inflection and stuff like that, and how that can relate back to our original function. So for example, let's say you have f of x is equal to 1 over 12 x to the fourth plus 1 over 6 x to the third minus x squared plus 18, right? Here's what I want. I want you to, 1, find critical points, and 2, find points of inflection, and 3, I guess as part of the critical points, determine where f of x is increasing or decreasing, and as part of 2, determine where f of x is changing at and increasing or decreasing rate. Okay, so take a second, hit pause, and come back and I'll work it out with you. First thing you're going to want to do is probably derive it, right? So f prime is equal to 1/3 x to the third plus 1/2 x squared minus 2x, right? If you're going to do this, you might as well factor it. These numbers aren't the nicest to work with. So what I'm going to do is I'm going to do a little bit of magic, okay? If we multiply by some number k on the outside, then we have to divide by k on the inside, right? And vice versa, right? If you multiply by k on the inside, you should divide by k on the outside, right? If you notice, this is 1/3 and this is 1/2. If you multiply both by 6, you get a whole number, okay? So what I'm going to do is I'm going to multiply the inside by 6 and divide the outside by 6, okay? So I'm going to end up with 1/6 and multiply the inside by 6. That gives me 2x cubed plus 3x squared minus 12x, like that, okay? Then I'll factor out the x. 1/6 x 2x squared plus 3x minus 12. I'm going to use the quadratic formula, which is going to give me negative b plus or minus the square root of b squared minus 4ac. Since c is negative, I'm going to swap the sign. The whole thing over to a, which is 4. Okay, it's going to give me negative 3 over 4 plus or minus the square root of 9 plus 4 times 2 is 8 times 12, that's 96, 105. Okay. So, and then we'll have so we'll hold on to this for later, okay? And also x equals 0, because we can't forget this guy, okay? So we'll handle that later. 2, we'll find f double prime, and I would not recommend using that to derive, because then you have to product, and that sucks. Use this, okay? And that gives you 1/3 times 3 is going to be 1, so x squared plus x minus 2, right? And this is going to factor as x minus 1, x plus 2, right? Because these two add up to the middle and they multiply to the end, okay? And that means we have our points of inflection at x equals 1 and negative 2, okay? All right, easy money. Now what you're going to do is you're going to make that sign chart again. Okay, negative infinity and positive infinity. Okay, the first thing I like to map in are my critical points. We can find the y values later. They're not the most important thing right now. Okay. So we know our critical points are going to be at 0. Let's put 0 right here. And then negative 3 plus this divided by 4. Okay, a little bit of magic. This is going to be a little bit greater than the square root of 100, which is 10. Okay, so we're going to eyeball it. We're going to say this is going to be negative 3 plus a number a little bit less than 10 divided by 4, which is going to be 7 over 4, which is like a little bit more than 2. Okay, so we're going to put this as negative 3 plus the square root of 105 over 4, which we know is going to be, sorry, a little bit less than 2. The less than 2 is important so we can do some approximations later, okay? Similarly, if we were to subtract, right? Again, this number is a little bit more than 10, okay? So negative 3 minus 10 is negative 13, and the whole thing over 4, and that's going to be a little more than negative 3, okay? So, or a little bit more negative than negative 3, okay? So this is going to be negative 3 minus root 105 over 4, which is less than negative 3-ish. Okay? All right. So now what we're going to do is we're going to go in and actually just do out the sign chart, okay, for our critical points. Okay? For critical point purposes, I would recommend plugging it into here. Okay? So if you were to plug in a very, very negative number, right? This will be negative, this will be a big positive, this will be a little negative, this will be a little negative, which is going to be negative. Okay. Okay, so now that next section, right? I'm gonna choose like -1. Okay, we're gonna choose -1 because I know it lives in here and it's definitely less than this. Okay, if I choose -1 and I plug it back into the derivative, right? I guess back into here would be better, right? If I have a negative number here, and then this will be positive, negative, negative. Okay, so this will be positive plus a negative number plus a bigger negative number. Okay, if you want to do that, please do. This will give you -1, 6, 2 minus 3 minus 12, and that is absolutely a negative number times a positive negative number times a negative number, which is a positive number. Okay. Again, if you don't feel comfortable approximating, don't do it out. Okay. I'm lazy. I'm going to approximate. Okay. And then from 0 to slightly less than 2, I'll choose +1, right? And I'm going to say, let's see, if I choose +1, it'll be 1/6 times 1 times 2, which is 2, plus 3 minus 12. That is absolutely a negative number. Okay. And then I'll choose like 100 or something. That's going to be positive. That's going to be positive. Positive times a positive is a positive. You end up like that. Easy money, right? Okay. So now what we're going to do is we're going to handle the points of inflection. Okay. Again, it behaves the same exact way as your critical points. Okay. So your points of inflection are going to be at -2 and +1, just for reference purposes, so I don't put this like -2 all the way out here. Let's put -2 right here and +1 at like here. Okay. All right. Now we're gonna plug in a number less than -2. Okay. I'm gonna choose -10. I'm gonna put into the factored form. Okay. F double prime of -10 is going to be a negative number times a negative number, which is positive. Okay. I'm gonna put it at the bottom so it doesn't interrupt the other stuff we've worked on. Okay. I'm gonna choose a number between -2 and 1. I'm gonna choose 0 because 0 is a nice and easy number to work with. Okay. And that's going to be a negative number and a positive number, which is negative. All right. And finally, we're going to choose a very big positive number. I'm going to choose like 10. That's going to be positive and a positive, which is positive, just like that. Okay. All right. Now that you have all your pieces, we're going to bring back that. And here's what we're going to do. Okay. We're going to be able to very loosely reconstruct the graph of the original function, the graph of this guy right here, using nothing but that. Okay? It's gonna be very, very cool, in my opinion. Okay. So if we were to put this into a proper, honest to God graph, right? Let's say this is our graph. Okay, ready? Here's what you're gonna want. So I'm gonna do that so it's not as glaring. So what you're gonna want is you want to separate your graph into all the parts, into pieces that your critical points and points of inflection naturally separate it into, okay? And the reason is because, for example, right here, right? Although your point of inflection doesn't change, right? It changes over here, your critical points change, right? The direction of your critical value changes. So there's a natural cutoff here, right? In the same way, right? Your critical value doesn't change here, but it does change for your point of inflection. So you want to separate there, okay? So like that, and like that. You draw it a tiny bit smaller and more transparent so you can see a little bit better. Okay, so now that you have your graph, what do we know? We know that from negative infinity, we're going to be decreasing at an increasing rate. So decreasing at an increasing rate looks kind of like that, right? It's more extreme, it's more dramatic, as opposed to like this, which is constant, or like this, which is gradual, more, right? You're gonna kind of that, right? Draw a line there. And then all of a sudden we change to increasing, right? At a increasing rate. increasing and increasing looks like this, right? I'm gonna spike it back up. And at two, we change, right? At two, we're going to be increasing at a decreasing rate. Increasing at decreasing looks like that, right? More gradual again. So we're going to kind of taper it back out, right? And then we find, oh, from 0 to 1, we change to decreasing, or we are decreasing at a decreasing rate. So decreasing at an increasing looks like this, decreasing at a decreasing looks like that. More smooth, right? So it's more dramatic up here, more smooth around here, right? And then here we are decreasing at an increasing rate. Decreasing at increasing is more dramatic, right? So we'll kind of curve it down even more. And then all of a sudden at here, we find that we are increasing at an increasing rate, which is more like that, more dramatic, right? So, and if you Desmos it, that basically is what it looks like. Now, there's a bit of a caveat in that we don't have the vertical shift, right? We know f of 0 is 18, so we know that this should be 0, comma 18. Okay, that's it. That's how you do these. It takes a lot of practice. I'm still pretty bad at it, and I freak myself out all the time. But yeah, do some practice problems, you'll be just fine. All right. Hey, thanks. Bye.